I'm going to introduce our next speaker, and the next speaker is Sean Parent. Sean is a principal scientist and software architect for Adobe's Mobile Digital Imaging Group. He's been at Adobe since 1993 when he joined as a senior engineer working on Photoshop and later managed Adobe's Software Technology Lab. In 2009, Sean spent a year at Google working on Chrome OS before returning to Adobe. And from 88 through to 93, Sean worked at Apple, where he was part of the system software team that developed the technologies allowing Apple's successful transition to PowerPC. Not many people know that Sean was a ski instructor when he was in high school. He also created the Actions feature in Photoshop, and Steve Jobs himself gave Sean a PowerBook for his help with the OS X launch. And as a no-nonsense man, Sean has chosen a very short and very telling title for his talk, Better Code. Let's have a big hand for Sean Parent.
Hey, thank you. This talk I first prepared for ICPC, which is the International Conference for Program Comprehension. And for people who don't know what program comprehension is, it's basically the study of how we understand software and tools for building software. It is not my field of study. It's not my field of expertise. But in putting this talk together, I thought I would take some time and ask friends about how they learn about a new software system when they jump into it. To give you a little background on my talks, I've been slowly working on a book called Better Code. This came out of some two talks that I gave at Going Native a few years back, and they were very well received, and so a lot of people asked me to write a book. So this talk is somewhat an overview of all of these talks. So this would be the preface. And tomorrow we're going to be talking about concurrency, which is kind of jumping to the end of the book. So we'll cover both of those. How many people know what the knowledge is? Anybody? One person? One person knows what the knowledge is. Somebody who's been to London. So the knowledge is a test given to the London Black cab drivers. Before you can become a London Black cab driver, you have to pass the knowledge test. And that means that you need to understand the city of London very well and what the routes are from A to B within the city very well. And I think the way that people learn about anything of scale has a lot of similarities. So when I go and I ask my friends how they learn about software systems, these are some of the answers I got. They said, well, I find some piece in the code and I trace through from that point to some other point in the code. And so I follow along a road and I see what happens along that road. Okay? And that gives me some insight into what's going on in the code. And other people said, no, don't trace through it. Just take a subsystem of the code and study it and kind of see all the ways that you can come in and out of this one location. And that will give you insight into the code. So you'll get a little glimpse. And some people said, no, just take a file, right, and learn everything in that file and then work through all the files. And that's like taking, a burrow here with very sharp edges and understanding that piece. But when I thought about, I think all of these are valuable ways and valuable tools for how you learn about a piece of code. But when I thought about how I do it, I thought none of those answers are right. This is kind of how I learn a piece of software, which is to say I study the system from the outside and I build up a set of abstract rules about how that system would have to work to satisfy those behaviors. Okay? And if you look, this is the London tube system, a map of the tube system. If you overlaid the tube system onto an actual map of London, you would get that. Right? There's not a strong, direct one-to-one correlation between your map of the tube system and where those tubes actually go. It's an abstraction that lets you stand back and understand the system as a whole. So let's take a look at how we apply these things to software. The first thing to understand about software is there are rules. Okay? There are rules that govern the behavior of software systems. And the rules sometimes exist outside of our code. This is an implementation of STD lower bound. Okay, how many people know what lower bound does? The rest of you have to go read. Lower bound is one of the most important functions in the standard template library. So lower bound is a binary search. It will give you the lowest point in a non-decreasing sequence where a new element could be inserted to keep the ordering. Right? So if you had 1, 1, 2, 2, 2, 2, 3, 3, 3, and you wanted to insert a 2, it would tell you the first point where that could go between the first one and the first 2. Right? So this is that binary search. Okay. But the code doesn't tell you everything about this. There's requirements on these types. Okay. So we have forward iterators here, which are just template arguments, and those come along with both a set of syntax that needs to go with that and a set of semantic requirements that go with a forward iterator. So we know that first to last here has to be a valid range. That means that if I start at first, if first doesn't already equal last, then every time I increment first, I will progress until eventually I hit last. I will never end up in a cycle and keep cycling infinitely. There has to be some path from first to last for this algorithm to work. The comparison function for this algorithm to work has to implement a strict weak ordering. Okay, how many people know what a strict weak ordering is? Far fewer. Okay, so strict weak orderings are very important in almost all of STL. If you look at the requirements of sort or lower bounds, these require strict weak ordering. What we mean by a strict weak ordering is that it is strict in the sense that it is not a partial ordering, that an element is either greater than, less than, or equal to the element being compared to. I should say equivalent to, because the weak part is that it's not necessarily a total ordering, right? If I'm sorting a bunch of records by last name, then all of the Smiths are equivalent. John Smith is equivalent to Bob Smith. Okay, so that's how it's weak. Okay, so a strict weak ordering is very similar to a total ordering, but it's not quite. The equal there is equivalence and not equality. Okay, so that has to be true. Okay, so in that comparison has to be a strict weak ordering for all of the values within that sequence. And there's no good way to verify that. There's no assert that you could write on that comparison to double check that it's a strict weak ordering. You would have to compare every element against every other element and then check those results, right? So you would end up with a huge number of permutations if you wanted to try to validate that. Okay, and then our value type has to be the same type as the dereferenced forward iterator type. Okay, or it has to be one I can have an asynchronous or an asymmetric compare function, in which case my value type has to be comparable to the items in my list and still maintain that strict weak ordering. So you have this whole set of requirements in just a simple piece of code like this that stand outside of the code. So how does this relate to software understanding? Well, I do a lot of desktop software working at Adobe. I've worked on Photoshop and Lightroom, a number of products. When I approach a piece of software, I always start from the outside if I need to understand a piece of software. So this is a menu taken straight out of Microsoft Word, not an Adobe product. Okay. So looking at this menu, one of the first things that I see are that some of the items are disabled. right? So I have some items that are enabled and some items that are disabled. Okay. So anybody know what the rule would be for disabling a menu item? I have one person. Right. Right. So the answer was maybe this menu item doesn't satisfy some of the conditions or requirements. Okay. So a little more formally, we can think of each of these things as representing a function, right? Some command, some function that's going to be executed. And that function has a set of preconditions and a set of arguments. Okay. And those arguments are coming from someplace. They're coming from the state of the application. So whether or not one of these menu items is enabled or disabled is whether or not the arguments to the function are satisfied. Okay? Whether or not the preconditions of that argument, the precondition of that function, whether or not the arguments being supplied satisfy that precondition. Okay? So we can think about it this way, right? We've got some function that the menu item is going to invoke. And we've got a predicate, P, that's telling us whether or not the preconditions for that function are satisfied. And that's telling our menu whether or not to be enabled or disabled. But these things have to be evaluating and executing something. So my application has some state somewhere, right, which is feeding in to this precondition. And that state is also feeding into my function, right? So if the state satisfies the precondition of my function, then P will be true, my menu item will just be enabled, and I can invoke my function. Okay? People following so far? Now, with this little diagram, I have a problem, a small problem here, right? Anytime you start to lay out dependencies and you have two arrows feeding into one place that originate at one place. In this place, I have my state that goes through my predicate, that goes to my menu item, that goes to my function, and my state also goes directly to my function. Okay? So that's called a join, right? That's a join in my graph where these two pieces are coming together. Okay? Now, for that join to be correct, that means that the information that comes along both of those paths has to match. If I'm coding in an asynchronous system, okay, if my state can be changing asynchronously, or my menu items are getting evaluated on a loop in my main UI thread or something like that, I need some way to ensure that those match, okay? And more importantly, I need some way to think about this system to know that every time I look at that, I have to make sure that those match. The other thing that I have is my function is coming back and modifying my state, okay? And that's creating what maybe is an infinite cycle, okay? And so that's a bad way to think about it. So I'm going to refine my diagram a little bit here. And I'm going to say, no, I've got my state, okay, which feeds in to what is partially my predicate now, okay? But I'm going to use a trick from category theory. How many people have done any functional programming? A couple people have done functional programming. Okay, so you might want to read some of the blog posts from Bartosz, and I'm going to butcher his last name, Milowski. Yes, Bartosz's blog post on category theory. But this is an instance of a Kleisli category. So what we're going to do is we're going to take our state, and instead of just evaluating it with a predicate and our predicate returning a Boolean, okay, our predicate now is changing into a function which is going to take the state and augment it by attaching a Boolean to the state, to the arguments, to our function. And so now what we have going up into our menu item is all of the arguments to the function plus a Boolean that says whether or not they satisfy the precondition. And so now I can think of my menu item as being a latch in the gate, okay? And it can say, oh, okay, the predicate says that these things are good, so I can open the latch, and when the user picks the item, I can let that flow through and go and execute the function. And because those now originated from the same place, I know everything here is going to be consistent and execute correctly. And then finally, I'm going to think about my function as not going down and modifying my initial state, but returning a new state, my state prime. Okay? And so now what I've got going on here with my hard lines is I've untangled this cyclic thing with joins into something that's a nice simple DAG that's going to progress forward, okay, in a very predictable way. Now, in going through this mental exercise, what I'm doing is I'm understanding how this piece of software must work. What are the rules that govern this piece of software? I know perfectly well that Microsoft Word is not written this way. Okay? I know perfectly well that it's probably following some model view controller pattern in how it works, or if it's Microsoft, maybe it's MVVM. Okay? But all of these components have to exist within that system for it to be correct. So now if I'm plopped into the code and I'm looking at a bug, maybe in the code, and the bug says this menu item isn't enabled when it's supposed to be under these conditions, I'm not just going to go blindly and add an extra if statement and say, oh, fine, I'll make it enabled then, whatever the bug report says, right? Whatever QE said. Now I can think about, okay, this predicate that's being evaluated has to correspond to the preconditions for my function. Let me go look at what are the actual preconditions for my function. Maybe it's the bug report that's wrong and that the menu item actually shouldn't be enabled. Okay? So I know what the correspondence are and I know what has to work. And if things are getting out of sync where previously I had the join, I know, oh, I see what's happening. I've got this information coming along two paths and this information is no longer consistent. And that's what the information is. It's the bug wasn't that the menu item was disabled when it should have been enabled. It's that it's still disabled, but it should be enabled now because my state has changed and these things have become out of sync. Okay? So by understanding what the rules are that actually govern the system helps me reason about the code. And as I'm in there reading the code, I can start to see, oh, I see. This piece of code plays this role in this diagram. Okay. So that's the menu item. That's how I think about it. Now, this talk is titled Better Code. In order to write better code, I think it's very important that we understand what good code is. Okay? And there's kind of a classical definition, which is that good code, correct code, is code that matches the specification. All right? How many people learned that in school? How many people had an instructor say, your code has to match the specification? Nobody? You guys went to different schools than I went to. It was like everybody. In any case, if you even look online, you'll find that that's the classical definition. Good code is correct. Correct code means the code matches the specification. It's somewhat true, but it's not the whole story. Okay. So what do we mean by correct? I mean correct in a mathematical sense. Consistent, without contradiction. So let's take a look at a piece of code here with a very simple bug. I hope everybody can spot the bug here. Right? Right. What happens if I execute this? Anybody? Yeah. Yep. Bad access. SIG abort. Okay, that's the actual error I get. Okay, why? I've got print string that's going to print a string, and I passed it a null pointer, and it didn't check for a null pointer. Okay, so there's a bug. But what's the bug? Okay, should I be checking before I dereference my null pointer? Should I be checking before I pass a null pointer? What's that? The while loop should be changed to check. Yep, so one vote is to change the while loop, to change print string to check. Okay. So, yeah, so what should you do when you're asked to print null pointer? Okay. here's my fix. Okay? So all I did was I changed my intention. Right? I changed the specification. I said, I want to crash. Force crash. Okay. There's still a bug though, but now the bug's much more subtle. Anybody want to hazard a guess as to what the bug is here? What's that? Incrementing s? No, it's a pointer to a constant character. S itself is not constant. What's that? It's not crashing unconditionally. That's the right answer. The standard doesn't guarantee that this will crash. Okay, it might launch missiles somewhere. It's undefined behavior. Okay, so now I've got a contradiction, but my contradiction is with the standard, not within the code. Defects can get very subtle in a piece of code. Consistency requires context. Consistency within a system means that you're looking at the system as a whole. Okay? And it's very easy to write a little function, a little piece of code, and think about, okay, I believe that this little piece of code is correct. Okay? But consistency requires that you're looking at everything. Now, even the standard and even Alex Stepanov don't always get things like this correct. So this is an abbreviated version of stdmin out of the standard library. Okay, so there's the definition of stdmin. And here's the definition of stdmax. Okay. Now, who would believe me if I said the definition of stdmax is wrong? One person. Two people. Oh, a few people. What's the problem with the definition of stdmax? It's not consistent with min. It's very consistent. They both return the first argument when the arguments are equivalent. Okay? stdmax should return the second argument, right? If I called min and max with the same argument, a and b, potentially they would both return the same thing, right? So that's a bit disconcerting. And it starts to affect other code, right? You don't know how much code I've seen that has a clamp function. Now clamp is actually going to be part of the standard, and it's defined correctly in the standard. But how much code I've seen that implements clamp like this. Okay, this is a bad implementation of clamp. Okay. So clamp, for people who don't know, is effectively a median of 3, right? It's supposed to say, given 3 values, give me the middle one, right? So it's clamping a value between a high and a low. And it looks like that's how you should write it. Max, low, A against min with high. Okay? And if you got a custom comparator, it would look like that. And here's how that fails. Okay, we talked a little bit about strict weak ordering before, right? So here I've got a low value and a high value, which are sorted 1 and 2 by the second guy, and I want to clamp OK between those two. Okay, so OK is between those two, right? So it should return A. But it doesn't. It returns low. Okay, so because of the asymmetry between min and max, right, people write bugs like this. Now the fix is you can rewrite clamp like this, but that's a pretty non-intuitive way to do it, to say, oh, I see, what I have to do is I have to put my argument that I want between the two first, instead of in the middle. Okay, so this is what the definition of max should say in the standard. Now, one problem is, once something like this is wrong in the standard, it's very difficult to fix, right? You're not changing the signature of max, and so if we go and change the definition of max, then everybody who had a correct clamp, we just broke. Okay. So once you get more and more arguments in here, you can start to see why this is true, right? If I have max of 3 arguments or max with with variable number of arguments, I want it to be the last thing, the greatest thing in the list. Okay. Now the other problem that we come to with rules, right? Rules can be subtle, they can be hard to spot, rules can be contentious. It was mentioned in my bio, I worked for a little over a year at Google. While I was at Google, I had this long-running argument with Craig Silverstein, who at the time had ownership of the C++ coding guidelines for Google. And this was from a message that Craig wrote to me. Okay. Now, I have lots of disagreements with Craig. I do have a lot of respect for the man, so don't think that I'm slamming him too hard here. But I'm going to let you read that for a moment. Okay. So what he's saying is, because everybody comes up with their own definitions for words, we shouldn't have any standard definitions for words. Right? Because everybody uses language a little bit differently, we shouldn't define what the language means. Right? Right? I view that as a big problem, but I see this a lot. People want things to mean what they want them to mean within the context within which they're using them. And that's a problem when you're working on a large software system. So, there is no spoon. One area where this comes up over and over and over again is dealing with zero. Okay. I'm pretty certain that the first person who went without a meal for a day understood the concept of zero, of nothingness. Right? But as mathematicians, it took people an incredibly long time to come to grips with zero. Right? If you look at the history, you start to see zero appear first in the Hindu tradition and then in the Arabic tradition. And it's not until Fibonacci in 1202 where zero starts to appear in Western writing on mathematics. Okay? And it's not until the 16th century that zero becomes part of common everyday experience. Okay? So from the first guy who went hungry in a cave to the 16th century is a long time to come to grips with zero. Right? Why is zero so hard? Well, as computer scientists, we still struggle with it. We still despise zero. What do I mean by that? Int x. Okay, what's the value of x here? That's right, indeterminate value. Undefined. Int x equals 1 over 0. What's this? Louder? It's a crash. No, undefined behavior. Maybe it's a crash. 1.0 over 0.0. Anybody? I heard a nan. Nan? Anybody going to argue with nan? May crash. It's infinity. It's not nan. Okay. 0.0 over 0.0. You were just a little too early. That's a nan. Okay, I can declare an empty struct. The size of my empty struct is 1, defined by the standard, not 0. Can I do that? An array with 0 elements? Yeah, this guy got the answer right. He said in the standard you can't do it, but in most compilers you can, which is true. That should be an error. But it's a common extension, so Clang and GCC will actually accept that by default. Which means that I can do this. I can create an empty type, okay, with just a type def to int 0. Now the whole argument around making empty classes be 0 is that every type should have a unique address. But the ones I can have an empty type, I can create an array of 2 empty types, and they both have the same address. Okay? And the world doesn't unravel. I can write a function, okay, that returns void, and I can actually say now in the language, returns void. That's okay. What about that? Can I do that? Anybody? No, that's an error. Okay. But void star, well, that's a pointer to anything as opposed to nothing. Okay. Let's say that I take a vector and in the middle of inserting something into my vector, I throw an exception. Can I output the size of the vector when I catch it? What does the standard say? Yes, no? Yes. Yeah, basic exception guarantee, valid but unspecified, okay, is what the standard says. So I can output the size, but I have no idea what that will print. Okay. I move an object into Y. My move from object X is also valid but unspecified. Okay. All of these places where we're looking at these things have a similar thing. We're uncomfortable dealing with 0, so we tend to patch around it. We disallow it. We make up answers. Okay, maybe it's infinity. Okay. We create a new value for our doubles called a nan to hold it. We continually try to sidestep it. This is because good code has meaning. Right? So what is meaning? Meaning is a correspondence to an entity, specified, defined. Okay? That's what the definition of meaning is. Okay? So the meaning that something has is imbued upon that object by how it connects to other things. Right? It's the correspondence. So when I put up this diagram, the meaning of my predicate is that dashed line. Okay? That predicate represents the preconditions to my function. That's the meaning of that predicate. Okay? And there's no place where that dashed line is going to appear in a piece of code, but that's the meaning of it. So these things, the absence of something, we've come to grips with pretty well. Like I said, the first caveman understood this, right? We know what 0 is. We know what the empty set is. We know what an empty range is. We know what the empty type is, void. Okay. The problem that we have with these things is that they tend to lead to the absence of meaning, right? Nan is the absence of meaning. It's nonsense. Okay? Nan is no longer a value. It's this thing no longer represents something else. Okay? Undefined is another word for has no meaning. Indeterminate is another word for has no meaning. Okay? An object that's in an undefined or indeterminate state has lost its correspondence to its value. So if we think about those things in mind, if we keep those things in mind, we can start to think about how do we deal with 0 consistently, right? You can't just brush it under the rug, right? You can't take and say an empty struct, I'm going to call it 1 and think that that somehow sidesteps 0. All it does is pushes the problem down to the next guy to deal with. Right now you get things like compressed pair. How do you get that 1 back out of there? Because you know it doesn't really take up any space. Right? So int x. Right? Alex Stepanov coined this term ages ago, but it's written down in Elements of Programming, if you've seen the book, which is a partially formed type. Right? The idea with a partially formed type is I can assign a new value into it, or I can destruct it. Okay? Those are the only two things that I can do. Why? Because those are the two things that restore meaning to the type. So when I have a type that's in an indeterminate state, which is what x is down here, another way to say that is it's partially formed. Before I can deal with that type, okay, I need to assign a value to it or destruct it. Okay? Compilers understand that pretty well. Most compilers, if I tried to use x, okay, if I said y equals x plus 5, they would at least give me a warning, if not an error, that said you were using x and it's in an indeterminate state. Okay, which means that x plus 5 doesn't mean anything, so stop it. Okay, 1 over 0, right? Undefined behavior, right? Why? Okay, well, 1 over 0 itself creates a temporary that's partially formed, okay? And so what I'm doing is I'm reading from that, and the compiler should ideally give me an error. X equals 1.0 over 0.0. How do I feel about that? Right? It was infinity. I'm actually going to agree with the standard on this one. I think infinity is the right answer. Actually, I should say it's an approximation for overflow. Right? I got an error in my slide there. Right. 0.0 is a nan. It's okay, but I would prefer that I get an error from my compiler if I then attempt to read from it, right? Catch it statically. Now, what could we do with an empty struct, right? One of my recommendations has been that we introduce a little bit of new syntax that says let us inherit from void, okay? If I want to say something that's really empty, okay? Any type should be able to inherit from void, which basically means that I have a zero-size base at my root. The reason why I can't just change the definition of empty is because I would break a whole bunch of code. Okay, that would give me size of empty as 0. What about int a of 0? Well, it's a standard compiler extension, and I actually think they're right. That should be okay. It should not be an error in the language. And especially since the standard should follow along with common practice, and given that we have two of the most major compilers that have been doing this for ages, and the universe didn't unravel in response for us having empty types, I think that's the correct answer. Okay. That should continue to be okay, but this should also be okay. If you've ever written template code that has to specialize on 0, or it has to specialize on type void, it's really a pain in the butt. It's really a pain that I can't deal with something that returns an integer and something that returns void consistently. Void star, that's okay. Here. So I disagree with the standard on this one. I think x should be declared as partially formed, and reading should be undefined behavior and preferably catchable from the compiler. The problem that I have it being valid but unspecified is that means that reading from it potentially has no meaning. And what I'm doing is I'm pushing to runtime something that is not easily checked, something that could be checked at compile time. Same thing here. Here I think the standard actually does more harm. Okay? By saying that the value within x is valid but unspecified means that the value x has to satisfy all the preconditions that are on that class, all the invariants for the class type. So So the problem with that is in real cases, that requires that you do an allocation at the time that you move from, which means that move becomes a potentially throwing operation. And if you look at all the backflips that the standard committee went through trying to define what's the state of a variant if I throw an exception trying to put something into it, right? You end up with a variant being it can be of type A or B or neither, because I have no way to get an object back into it, okay? That's just one sign of the damage caused by a wrong definition of what move means. Makes you wonder. Take chicken, for example. These are all movie quotes if you haven't seen them. So this issue came to me recently. Jonathan Coe wrote a proposal for the Standards Committee, and this is a very simplified version of it. And this was the meeting, the Oslo meeting, just before the Issaquah meeting here. And this is a very heavily shortened version of the specification. Okay? But he proposed that we had a new pointer type called clone pointer, okay? Which is like unique pointer, but with two additional operations. Okay? One is that when I copy the clone pointer, right, a unique pointer is not copyable, but a clone pointer would be copyable. And when I copy a clone pointer, what that means is I'm going to copy the thing the clone pointer points to. And so my new pointer will point to a new instance of that thing. Okay? And when I assign to it, same thing to be consistent with my copy, now I will copy it and end up reassigning my pointer to point to a new thing. Jonathan took this to the Standards Committee. I was not at the Standards Committee meeting, but my understanding from Jonathan was he took it, he presented it, people in the room said, this makes us feel very uncomfortable. When he asked why, they said, well, we're not sure what the semantics means. And when he said, what does that mean? The answer was, go talk to Sean. So Jonathan sent me an email and said, what's wrong with this? Anybody know what my answer was? Anybody? Does this look like a good definition for a type to you? Okay, it's not. So there's a lot of things wrong with just this little definition. Right? Well, that's just a note saying what my copy assignment is. Okay, here's the problem. What does it mean to copy something? Right? What it means when we create a copy of something, right? And this is an English word, right? Not a computer science word. What it means when we copy something is that we create something which is equal to but disjoint from the original. Okay? So if I copy my bottle of water, I end up with 2 bottles of water, and if I drink this one doesn't get drunk. Okay? So that's what copy means. That's the meaning of copy. Okay? Your compiler relies on this meaning of copy because your compiler can elide a copy, right? Your compiler can come along and say, oh, hey, he said to put this function result into X. I don't have to copy the object into X. I can just elide that copy and construct it directly in place because I know that that's going to give me an equal object to the original. Okay? So that's the definition of copy. Okay? Well, what happened with this clone pointer? Right? Clone pointer was just like a unique pointer, and unique pointers I can compare for equivalency, and what that does is it compares the 2 pointers, but now my clone pointer, when I copy my clone pointer, copies the object it points to, and so if my comparison just compares the 2 pointers, now I have an instance where copies are not equal to each other. So could we fix it? We could. We can be a little sneaky here. Okay? We can say that what we want are the copies should be equal, and that would imply that we were actually comparing for equivalency the 2 objects that were pointed to. But those 2 objects may not implement equality. And so what we're going to do is we're going to define copy to say that the copies are equal, but on our clone pointer now we're going to modify it and remove the equality operation. We're going to get rid of equality, right? So we're going to cheat. The next issue that I have with this type, what does it mean for something to be a pointer to something else? Right? Okay? So what it means is that the primary purpose of that object is to be a reference, an indicator of something else. Okay? Which means that if I have two pointers which are equal, what that means is that they point to exactly the same object. But I just said that a clone pointer, because when I make a copy of a clone pointer into another clone pointer, that equivalency has to be deep equality. Okay? Otherwise, it's not a copy. Okay? Then that also means this is no longer a pointer. Okay? I've lost the semantics of being a pointer. Okay. That's what happens, right? So I make a copy. It implies that they're equal, but the addresses of the things they point to is not equal, which means they're not referencing the same object. So it no longer has pointer semantics. Okay, so what am I going to do now? Well, the only place I had pointer in here was in the name, so I'm going to rename the thing, right? The name that Jonathan and I came up with was indirect. In Issaquah, the Standards Committee thinks that polymorphic value is a better name. So I think they're okay on that one. I somewhat disagree because I think this is a useful type even in the absence of polymorphism. Okay. Here's a subtle issue with the item. I didn't see this one right away. So this came up in conversations. If I've got this thing that was a clone pointer, now it's an indirect, and it points, still kind of refers indirectly to another object. Okay. If I have a const instance of one of those, what does that mean? Does that mean that const propagates to the remote part as it does like with an STD vector? If I have an STD vector, even though the elements in the vector are heap allocated, if I have a const vector, I can't change the elements, right? It's not just the little local vector piece, okay? But a unique pointer I could. If I had a const unique pointer, I could still change the object pointed to. Okay. Well, to understand that, we have to define what const means, okay? So what const means is that const only allows read access to an object, and if all I do is read from an object, then I can't modify it. Okay? So if I read from an object, if I make a copy of an object, and then I read from one of those two copies, then they're still equal. Okay? And further, that if I had a function that was modifying A, that would not be allowed by the compiler. That's what const means. Okay. Well, with our indirect, as it's currently defined, right, we could write an indirect here called read, and it's const indirect, and we could modify star x, right, because this thing was defined in terms of unique pointer. So which means that I could end up where they're not equal. I can contradict myself. Right? So to fix that, I have to do const propagation. Right? So I can overload get on const, and my dereference operator on const, and my arrow operator on const. Okay? And so that's called const propagation. I will get that right. So that's const propagation. Now, which just basically means that if I can't modify the local part of my object, I also can't modify the remote part of my object. So these are the three changes that we came up with. And Jonathan took these back, and this is now making progress, this new type, through the standards committee meeting. But at least one person on the standards committee meeting was like, hey, wait a minute. This isn't what I wanted at all. Right? What I wanted was the type you originally defined, right? Which is one of these things that allows me to, that's very similar to a unique pointer, but allows me to make copies of the thing that's pointed to, right? Well, there's an alternative approach here, right? Anybody guess what the alternative approach is? Make a function, maybe, something along those lines. So it gets a little more complicated with polymorphism because the copy has to be type erased in the act. The alternative specification is to say that I have clone pointer, which is like a unique pointer, but with one additional operation, clone, okay, that works by copying the object pointed to. Example implementation of clone operation is right there. Okay. So I ran into this hole because I called it copy. Okay, because words have meaning. Words have meaning to us. Words have meaning to the compiler. They have semantics. Okay. So I once had an engineer walk into my office and say, I am writing a function for my class, a member function, for my class to copy my class. What should I call that member function? And I said, it should be the copy constructor. And he said, no, I already have a copy constructor that I'm using for something else. True story. It's a good way to get kicked out of my office. Don't do that. Don't do that because people reading your code are going to get confused by what it means. Okay? And don't do that because the compiler reading your code is going to get confused by what that means. So what's in the box? A lot of times people say, right, especially when we were looking at zero and lack of meaning and unspecified value, can't we create a system where something has meaning all of the time, where we never have a state where an object has lost its meaning? Okay? We can do better than C++ does, right? But there's a fundamental tension there. The tension is between safety and efficiency. Right? First thing, it's important to understand what we mean by safe. Okay? A safe operation is an operation that preserves meaning. Okay? An unsafe operation is one that potentially leaves an object in a meaningless state. Right? That is the definition of a safe and an unsafe operation. Okay? STD move, people hate me for this, STD move is an unsafe operation. Okay? The moved from object is left in an unspecified state. Unsafe doesn't mean bad. Okay? So that's the definition of it. So what happens here, if you're doing a permutation, okay, any permutation, STD sort is a permutation, STD rotate is a permutation, STD reverse is a permutation, stable partition, these are all permutations. Okay? They permute a collection of objects, rearrange them, you end up with the same objects you had before, but in a different order. Okay? So every permutation decomposes to a set of cycles. What does that mean? It means I move some object out, wherever that object is going, the object that was in that place goes someplace else, and so on and so on. Okay? So I can have one or more cycles in my permutation. Now if I want to do a permutation, that means I have to pull an object out to leave a hole into which I'm putting another object. And there's the fundamental tension. What's in the box? What do I leave in the hole? Okay? And what do I mean by that? Well, if I leave nothing in there, okay, then this sequence of things, right, has lost its meaning, and now my permutation is unsafe. Okay? But if I put something in there, okay, in the hole, I can regain my safety, but now that requires a write back, and it's inefficient. Okay? So STD move, letting me move an object out, attempts some level of safety by saying valid. Okay? But valid, in this sense, doesn't give us safety because the value is still unspecified, so it's lost its meaning. Okay? So STD move is an unsafe operation. STD move is also inefficient because it requires that I write back something into that state to ensure it's valid. Okay? So STD move is an unsafe, inefficient operation. Okay? People hear me say this and they say, Sean Parent said STD move is bad. I didn't say STD move is bad. Okay? Goodness and badness are not the same as unsafe, efficient, inefficient. Okay? Okay? It is what it is. Now, there's a duality, okay, between transformations and corresponding actions. Okay? A transformation is functional programming, right? I transform one type or one value into another value. An action is an in situ operation, operating on something in place. Okay? So for any action, I can write it in terms of a functional form, and vice versa. For any functional form, I can write it in terms of an action. Okay? So for all the functional programmers who think that functional programming provides this tremendous amount of safety, well, kind of. Okay? I can always transform one into the other. Both of these are Turing-complete systems, right? Right? In a Turing-complete functional language in Haskell, I can write a C machine and write all the stupid same mistakes in the C machine that I would write in C. Okay? I can always do this transformation. Okay? Why does it matter? Because one form or the other may be more efficient. It's not always true that the in situ form is more efficient than the other, but it might be. The most common example is STD sort. The most efficient way to sort is to sort in situ, to sort in place. Okay? That is more efficient than doing sort by making a copy. Okay? Functional programmers cannot write quicksort. So, it's not that I'm lazy, it's that I just don't care. Good code is efficient. Okay. Now, efficiency can be in time, in memory, in power, or in any other resource. Okay. And oftentimes as engineers, that means we have to make trade-offs. Efficiency means maximum effort with minimum resources. So, efficiency of a system is determined largely by its choice of data structures and algorithms, and its choice of what to optimize for, right? If you optimize for size resources over performance resources, that changes your efficiency. The operations that you have available, right, will determine the efficiency of things that you can do with it. So this is how, if I have bidirectional iterators, so those are supposed to be two iterators, pointing into a sequence, and I want to reverse it in STL, this is how STD reverse does. It just does pairwise swap all the way down. Okay, and so long as I have bidirectional iterators, right, even if I have additional capabilities for random access iterators, there's really no better way to swap. But what if I only had forward iterators? Okay. Okay. So what if I want to reverse the elements within a linked list, but I don't want to resplice my linked list, right? I want to reverse them in place. Can I do that? Anybody? So everybody should say, of course you can do that. More important question is, can I do that with some reasonable efficiency? Yeah, so you can kind of see the problem there as far as like, okay, if I can only go one direction through, I can make multiple passes through the sequence. How many passes do I have to make in order to reverse the whole thing, right? If I use that algorithm, it would be very bad, right? I'd be scanning all the way down to the end, doing a swap, scanning down to one short of the end, doing a swap, so on and so forth. But you can actually do it relatively efficiently. Okay. So here's the algorithm. This is mostly cribbed from Alex Stepanov's Elements of Programming book. This is not in the STL, should be in the STL. So this is how we do it, right? Basically, we're going to do a divide and conquer, And the way to think about it is if we did pairwise swaps, okay, of all the things, and then we built up and swapped a larger section all the way down, and if you kept doing that, you would end up reversing the entire sequence, right? In graphics, there's a very common trick that if you want to rotate something 90 degrees, and it happens to be square, you can treat them as like tiles on a board and shift all the big squares, like cut it into 4 squares and rotate them around by 1 notch, and then within each square do the same thing and go all the way down to a pixel level, and that will rotate your entire image 90 degrees. This is the same idea, it's just along 1 dimension. So here's how it looks. Here I didn't show n, the count. I just showed how the pointers move. Right? So if you execute that code, we come along and we do a reverse of a section like that. And now we're going to reverse that section because it's a recursive subdivide, and then we're going to swap ranges all the way down. And we end up with things in a reverse order. Okay? So it's O n log n and efficiency. So every place that I know of in STL where we have something that's defined for the algorithms that cut off at either random access or bidirectional iterators, we could actually provide implementations all the way to forward iterators that at least had O n log n. Okay? And I think most people think about efficiency in wrong terms. Especially young engineers, I will ask them to plot like order n log n, order n squared, things like that. And they tend to put like n log n like right between n and n squared. Okay, that's not how it works. N log n is log n is effectively constant, right? You're never going to end up with a log n that's, say, bigger than 64, right? For any size data set that you're ever going to encounter, right? So log n is effectively k. It might be a bigger k than you would like with just an order n, but it's a k. For all purposes, it's a k. It's a constant. Okay. So this is Microsoft Word again, right? So how do we think about the efficiency of something like this, right? Well, if I'm looking at something like Microsoft Word and I'm looking at the operations, I'm looking at, okay, well, I can type characters into the sequence, I can be inserting characters into the sequence, I can make selections and I can modify those selections, okay? So I might think in my head of a very simple thing where, oh, I've just got a sequence of characters, it's a vector, and I've got this very simplified view and a selection into that vector, okay? And I might actually sketch that out if I were trying to study a system and say, yep, I've got a sequence and I've got these things, but I also need to know what the complexity are of the operations that are needed for this to be a reasonable running application. Because in reality, I probably need a data structure that's something more like a rope, right? And the reason for that is I need something that resembles constant time insert into the middle of my thing, but I also need constant time indexing, okay? Which means a vector would give me constant time indexing, but not constant time insert. So a list would give me constant time insert, but not constant time indexing. A rope would give me log n operations for both of those, okay? So it will not be as efficient as either, but because I require both, I need a more sophisticated data structure. We've been talking about efficiency of operations, but we haven't talked too much about efficiency of types. Okay. We perfectly can. A lot of people don't think about types in this form, but we say a type is complete if it has sufficient basis operations so that I can get to any other value within that type, okay? Strictly through the basis operations, right? Through the public member functions for that type. That's a complete type. Okay? A type is efficient if I can do any transformation to get to any other value as efficiently as possible through those basis operations. Okay? Okay, so if I have an efficient basis, then I say I have an efficient type. Now, the easiest way to get an efficient type is to make everything public, because then by definition, you can get to any other value as efficiently as possible. However, you're going to fail to protect the invariance, and this would be a very unsafe type. Okay? So the idea is to figure out how you strike the balance on both of those. And again, my comment about std move being both unsafe and inefficient. And the very last thing that I wanted to say about good types is that they're reusable. Okay? So, reusable types. They can be concrete. A lot of people say, oh, Sean's a big template guy, so he wants everything to be generic. Not true at all. Okay? So a good algorithm that's very concrete can be very reusable. Numeric algorithms are a concrete example. Same with UTF conversions. Okay? So they should be generic when the algorithm is useful with different models. Okay? But sometimes it's faster to convert from one representation into another and perform the operation and to go back than it is to provide a generic implementation. I see people in graphics all the time coming to me and say, well, why don't we have like a, template to define a pixel type, right? It could be 8 bits, it could be 16 bits, it could be 16-bit float. There's different forms of 16-bit scalars. It could be 32-bit, right? Why don't we have some type like that? Well, most of what you'll find out is a lot of times it's more efficient to actually convert your image into a canonical form, perform the operation in the canonical form, and then convert back than it is to try to deal with it in place. Okay. Runtime dispatch is when the types are not known at compile time. That's the only time that you should be thinking about runtime polymorphism, is when you do not know the types at compile time. So you want to minimize the client dependencies and intrusive requirements. Separate your data structures from your algorithms, right? Too often I find classes where they've got a beautiful algorithm that's built in as a member function of the class, and I want to use that algorithm, but I want to use it with my own data type. The worst offenders of these are all the string classes, right? How many string classes do you see with built-in operations that have nothing to do with that representation of a string, but they're still useful ops? Along those lines, this is what a UTF conversion function is. I don't want a string class that's got a convert me to UTF-8, which I see in almost every code base I ever pick up. Everybody has their own string classes and their own member functions. I just want a standalone generic function that can convert between UTF representations. This is why I hope that this talk isn't going to waste, but I think it probably is. So this is my dark side here. John Bentley wrote this in Programming Pearls. Okay. In Programming Pearls, John Bentley went out and assigned 2 classrooms of senior developers at major corporations, IBM, Xerox PARC, really first-class people, and gave them a programming problem. And the programming problem was a binary search. Okay. And what he found was 90% of the programmers, given any amount of time, couldn't write a correct binary search that didn't have bugs. And in many of the cases of the remaining 10%, he wasn't 100% convinced of the solutions they provided. This is what we're talking about, right? Very concrete version, but it's effectively the same algorithm that I showed at the very start of this talk. Now, if you interview for the Photoshop team, you will be given a take-home test. And the take-home test is John's from Programming Pearls. It is to go home and write a binary search. Surprisingly, very few people pass it, even though I stand up in front of a huge number of people at conferences like this, and I tell them that's what to expect. Very few people pass it. And I find it very disheartening. But there are some signs of hope. For years, I worked with Alex Stepanoff on the book Elements of Programming, which is out, which I think is a wonderful book. It's a very difficult book, but I recommend you all get a copy and struggle your way working through it. I think concepts are a critical addition to C++. I was disappointed that they didn't make them into C++ 17. I think the current approach that was going into C++ 17 is the correct approach. But they're not dead yet, so they'll come along. I like the fact that there's renewed interest in new languages and new formalisms. Right? For a while, I thought language design was getting kind of stale and dead. There's languages like Rust and Go and systems like React and Angular and Haskell, which is both in the whole LLVM work and all the JavaScript transpiler work. So there's just a huge renewed interest in not looking at things the same old Java-ish reference semantic language style of solving problems. And finally, there's a rise in reactive programming and functional reactive programming. And if you want to find out more about why I think that's important, you need to attend my next talk tomorrow. So my work continues. I published a paper recently with Jaakko Järve with a very long title there on reactive systems. We put out another paper here on one way to select many, which is about how to deal with selections within user interfaces effectively and efficiently. Okay. You can always find my presentations at the link there, and there's a link to my GitHub repository, which has some ongoing research work there. But my conclusion is I want you all to go off after listening to this talk and write better code. Before I open it up to questions, which I will do in just 1 second, I do want to let you know that I'm staying here for the entire conference, so I'm not buzzing out. And I'm here for you, even though I enjoy attending talks and listening to talks. That's not why I'm here. So if you want to corner me and go pick my brain or talk to me or go get a beer or sorry to my wonderful hosts, I will even blow off a speaker lunch if I'm engaged in a conversation with one of the attendees here. Please do. That's why I'm here. I got my breaks in the industry because I had the nerve to go up and ask people who were very much more senior than I difficult questions. And that led to conversations, and that led to jobs and opportunities and new work. And so that's why I'm here, to play that role and to help you guys. So thank you.
I use the copy assignment operator to implement name parameters, which is not what it's supposed to be used for. Would I get kicked out of your office?
Yeah, you'd probably get kicked out of my office. Yes. People will sometimes abuse operators for things like that. They'll abuse them as a mechanism or things for DSL. I would like to see the language start to be able to rely on and enforce the semantics of the operations. For something like that, I don't think you're going to cause a problem. If we do go that direction in the language, we would certainly need a mechanism for you to say that, no, what I really meant was assignment, right? Because otherwise we would break all of your existing code. So I don't think it's a horrible abuse, and sometimes a little syntax sugar and a little bending the rules to break the mechanism are fine, and that's a totally different case than a clone pointer here. But you'd still probably get kicked out of my office.
I'd like to refer to your considerations about meaning. Wouldn't you agree that even if you had the best language possible, it would be still impossible to have all the meaning in it, and the only good solution is to develop the ubiquitous language in a team? And this must be something beside the language you're writing.
So, I think, yes, you cannot have a language where all the meaning is within the language. We can certainly do much better than we are. The idea of having things like a specification language or something that sits on the side is the equivalent of kind of double entry bookkeeping, if anybody knows anything about accounting. Okay, so what we tend to do is we can't say everything we want to say, but the more ways that we say it, the less likely we got it wrong. Okay, so if we say something in code, and we say something in English, and we say something in mathematics, and maybe we say something in a test case, if all of those things are consistent, okay, then we are way less likely that we got it wrong. And that's what we're trying to do. I would like to see more invested in things like, formal specification languages. There are some out there. There's Leslie Lampert's TLA work, which is quite good. A problem with those is they are way advanced and haven't filtered down to the mainline programmers, and unfortunately, I think that's where formal verification and thought is needed first. At lunch, I threw out a comment and said, "How many people actually, prove their code?" Right? Very few people do, and we're almost taught in school not to. Right? Everybody learns that you can't prove an arbitrary piece of code is correct or not, and we think that that's the end of it. But that's not the end of it. You're not writing arbitrary pieces of code. You're writing specific pieces of code to solve specific problems. And you can prove your code correct, and you can prove your systems correct, bottom up, taking them a piece at a time. And even if you don't write it as a formal mathematical proof, if you just take the time to put up front an argument in a comment that says, "This is why I believe this piece of code to be correct. These are my loop invariants. These are the invariants of this piece of code. Assuming all of this follows, QED, I should end up at this location." That's a way better place than we need to be. And if we could write that in a more formal but more approachable system, I think that would be wonderful.
Touches a bit on the previous question, but how do you view design documentation in conjunction with the writing generic code?
Yes.
And solving algorithms?
Yes. I think the two go together. Like I said, it's double entry bookkeeping. Right. You have to write down what it is that sort does, because the meaning of sort isn't in the code, right? All of the little things for my lower bounds where I said this has to be a valid range, that's all documentation. That's all part of the specification that has to sit on the side of it. So that has to be written. The mistake that I think a lot of people do is they think that there's an ordering there, that you write the specification and then you write the code. Well, you're actually way more likely to get the specification wrong and to have your specification be self-contradictory, and you have your specification be something that plain isn't implementable, okay, than you are to get the code wrong, right? The two get developed together, right? Same thing with people are like test first programming. You write your test cases first, right? Trying to figure out how to write an algorithm like sort by writing the test that says is sorted is a really bad way to try to learn to write sort. Okay? Is sorted gives you no insight into what it actually means to do the sort, right? So the test case has to evolve with the code as well, right? And so I view those as things that you should be writing test cases, you should be writing specifications, but you should be writing them in parallel. You should evolve them together. And ultimately, the purpose of the specification is so that you can give it to somebody else to read and they will understand what it is your code does. And if you're very precise, maybe how they would go implement your code to match that specification. But it goes together. So.
Okay, perfect. Thank you very much.
Yep.
Just for you to know, Sean and his code is getting better all the time, as the Beatles would have it. And Sean Parent will be coming back, so make sure that you show up for his better code concurrency session is in this room tomorrow at 1:30 p.m., which is after lunch. And for the time being, let's have a big hand for Sean Parent.